Hi everybody, welcome to our next video where we're going to get into the details of reaction mechanisms. In this video, I'm going to go through the particulars of one reaction's reaction mechanism, or at least its proposed reaction mechanism. But just to start, I want to show you some of the bullet points that we arrived at from the last video. Remember, mechanisms are hypothetical pathways about how we think we get from reactants to products. We can never be guaranteed that our theoretical reaction mechanism is exactly what's going on. We always need to rely on the experimental data. We're going to have experimental data about the reaction, and our proposal, our theoretical mechanism, has to match that data. And then we're going to now start to use these terms of elementary step, intermediate molecularity, and rate determining step. All right, so let me show you the reaction whose mechanism we're going to look at in some detail. So we're going to take a look at NO2 plus CO to make nitrogen monoxide and carbon dioxide. So in this reaction, it's been determined for us, our graduate student has gone into the lab and determined for us that the rate law is rate equals K, NO2 to the second, and you'll notice that in this rate law, there is no dependency on the concentration of carbon monoxide, CO. So think about that for a moment. If there's no dependency on the concentration of CO, what must then be the order of this reaction with respect to CO? Maybe you're thinking that the order with respect to CO needs to be zeroth, and you would be right. All right, so this is zero order in CO. So it's a reagent. It needs to be there for the reaction to happen, but varying the concentration of CO for some reason does not impact the rate of the reaction. The mechanism we'll come up with hopefully will explain why. So let's talk a little bit about what mechanisms are versus what overall reactions are. So this statement up here, the overall reaction, is exactly that. It's the overall reaction. And overall reactions, when you think about it, they're actually a thermodynamic statement. In other words, we know what we have before the reaction, namely these reactants, and we know what we have after the reaction, these products. So I have the before and I have the after. That's really what thermodynamics cares about. What was there before? What was there after? What are the big differences? That's thermodynamics. Kinetics is the part where we're going to start to study what goes on between the before and after. So in a way, we're going to fill in a whole bunch of details that would correspond to what's going on here with the reaction arrow. Exactly how does NO2 and CO combine to eventually form NO and CO2? That's what we're going to get at. All right, so we have our experimental data that the rate is equal to K times NO2 squared. When we propose a mechanism, and just for the record, we won't ask you folks to ever propose mechanisms. That's kind of above our pay grade right now, but what we will ask you to do is validate, vet, or kind of approve a mechanism. Basically, is a proposal a reasonable idea? And the two basic benchmarks that a mechanism has to pass to be considered a reasonable idea is, one, the individual steps within a mechanism. That's what a mechanism is. It's a series of individual steps. Those are going to be called elementary steps. Those individual steps have to add up to the overall reaction. And then the theoretical mechanism, when we analyze it, it's going to produce a rate law. That theoretical rate law has to match the experimentally determined rate law. So there has to be coherence between what the theory says ought to be true and what actually is true based on experimental results. So let's go ahead and take a look at the mechanism that's being proposed for this reaction. Now this reaction, if you take a look at it, at the end of the day, what it really is it's a transfer of one oxygen atom from NO2 over to CO to leave behind NO and CO2. So here's the proposed mechanism. Again, this is not something we would expect you folks to be able to come up with sort of out of thin air. We'll provide the mechanism. Your job is going to be to evaluate it. So let's just talk a little bit about mechanisms. Mechanisms are a proposal of a series of individual steps. These individual steps, these are the elementary steps. So these guys are the elementary steps. So I have two elementary steps in this proposed mechanisms. Some mechanisms have one step, some have 2, 3, 4, 5. Many mechanisms have very large numbers of steps. 10 or more steps could be a fairly complicated mechanism. So we have elementary steps. Another key idea that we have to talk about is the concept of intermediates. You'll see that during the course of this reaction, we eventually make NO3 during the first step, and then that NO3 is a reactant in the second step. So the NO3 shows up, and then it goes away. What do you think this is going to be referred to? Yeah, you probably get that. This is the intermediate. All right. This mechanism is being proposed as having only one intermediate. Other more complicated mechanisms might have many more. So there's an intermediate. The next term I'll explain is the one that sounded kind of funny from the preceding video. It sounded like I kind of made it up. Trust me, I didn't. The idea of molecularity. Now, what a mechanism ultimately comes down to being is this is a proposal for what we actually think is happening at the molecular level. So we're suggesting that an NO2 molecule bangs into another NO2 molecule to make NO3 and NO. And then later an NO3 bangs into a CO to make NO2 and CO2. That's what we think actually happens. The overall reaction is what eventually happens, but what we really think is happening are these steps down here. So molecularity is a property of the elementary steps. Namely, it's simply how many molecules are banging into each other during any elementary step. You see in both of these elementary steps, they both have two molecules, two particles colliding with one another. These kinds of elementary steps would be referred to as being bimolecular. Both elementary steps are bimolecular because they contain two particles banging into each other. Let's say in some other mechanism I had one reactant in an elementary step that kind of decomposed, so one thing falling apart. That would be a unimolecular elementary step, not mono, but unimolecular elementary step. Then suppose I have three things colliding during the course of an elementary step. So A, B, and C, for example, come together in an elementary step. That is going to be referred to as a termolecular elementary step. Not tri, it's ter. So we have uni, bi, and termolecular steps. All right, so that takes care of a lot of the nomenclature. There's one other term that I haven't yet explained, and I'll get to that as we start to interrogate this mechanism a little bit. So first thing I'm going to do here real quick is I'm going to free up some space here because I want to get a clean board. So let me just remove some of these ideas so we can draw some more on this one slide. Okay, so now we're going to start to evaluate this mechanism, and I had two benchmarks. Benchmark number one, the individual elementary steps, when I add them together, have to combine to give me the overall reaction. Think of this as like doing a Hess's law analysis with the elementary steps. I'm going to add reactions like you do in Hess's law, and we'll see what the result is. When you add reactions together, what should go away during the process of adding elementary steps? What kinds of particles should go away? The intermediate should go away. So the NO3, you see I have NO3 on both sides of my two different elementary steps, so they kind of cancel out. Also, I have an NO2, two of them on the left of the first reaction, and one on the right of the second elementary step. Those two will factor away. So I'm left with an NO2 and a CO on the left, an NO2 and a CO on the left, and then an NO and a CO2 on the right. So, in other words, this mechanism passes the first benchmark. The sums of the elementary steps add up to the overall reaction. So benchmark number one has been cleared. Now, the second thing that has to be true about this mechanism is whatever rate law this mechanism suggests, it has to match the theoretically observed rate law. Now, just to remind you, the experimentally observed rate law. The experimentally observed rate law was rate equals K times NO2 squared, and just for completeness, I'll put the CO in to the 0th. So really, it's KNO2 squared. So does this mechanism give that result? Does it theoretically add up to that experimental result? Well, now we have to talk about how we evaluate mechanisms for their rate. So again, I'm going to go ahead and clear some space here. Okay. So, in any series of elementary steps, we have what will be referred to as a rate determining step. Amongst all the elementary steps, one of them is going to be the bottleneck. One of them is going to slow down the whole works. So this isn't always true, but it's typically true that one step will be the slowest. I kind of make the analogy between this idea and, say, your commute here to school in the morning. There's always that one step on the commute here that might be rate determining for you. There might be a signal light, a left-hand turn. For me, when I drive to school, there's a T intersection. And if I get through that T intersection pretty quickly, I'm going to get to school fairly early. But a lot of times I'm backed up there, and it takes a good 5 minutes or so to get through that T intersection, so that kind of slows me down. So within the proposed mechanism, another thing people will need to propose is the rate determining step. And it has been proposed, for reasons that are, again, kind of above our pay grade, that the first step is the slow or rate determining step. And you can see within the mechanism here that each of my steps have their own rate constant values. That's what these little k's are. So this is the rate constant for the first step. This is the rate constant of the second step. So here's what this reaction would sound like if you could have put a microphone up to it. It sounds like this. Chugga 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 zoom. So the reaction goes very slow through the first elementary step because that is being proposed, that is what is believed to be slow, and then it zooms through the rest of the reaction after that. So as it chuggas through the first step, it gets to the end, and then it shoots over. So really, the speed of the reaction is going to be dictated by how fast we can get to the end of the first step. Because once we're at the end of the first step, we pretty much are done. We're relatively speaking finished after we get through the first step. So then what we're going to do is we're going to write down the rate law of the proposed mechanism based on the molecularity of the rate determining step. My goodness, that sounded like a mouthful. Here's what I mean. So the rate for this mechanism, rate will be equal to, which is the slow step? The first one is. So we'll use the rate constant from the first step. What is the molecularity of the first step? Well, it's all based on NO2. There are two NO2s in this reaction. So I could basically write each NO2 twice. And then that could be equal to K1 times NO2 squared. So I get to write down the rate law only for mechanisms, only for elementary steps, directly from the stoichiometry, also known as the molecularity, within the elementary step. Why? Because these elementary steps are what we literally believe is happening during the course of the reaction. We think an NO2 has to bang into another NO2 during the slow step. Therefore, if I mess with the concentration of NO2, I will mess with the rate of the reaction. And since NO2 appears twice in my slow step, it will have a squared influence on the reaction's rate. So it will be second order. So now we've begun to detail what order is about. Order of a reaction, order for the kinetic statement of the reaction, tells us how important within the mechanism that particular species is as part of a rate determining step or some other aspect of the mechanism. We'll see other influences of elementary steps in other mechanisms down the line. So this is then going to be our rate law as predicted by this mechanism. So then the question becomes, does this rate law, does this look like that? It sure does. The only minor difference is that here I just called it K, any kind of general K. Here we're calling it K1. But these are just constants, and I'm just giving them different labels. So the essential parts are the same. K, concentration of NO2 squared. K, concentration of NO2 squared. So, this seems to work. Does it add up? Do the elementary steps add up to the overall reaction? They sure do. And does the mechanism yield a rate law that matches the observed rate law? Yes, it does. By the way, there's a typo there. That should be NO2. So this mechanism works as far as both criteria are concerned. So that's the first example of us looking at a reactions mechanism and evaluating it, seeing if it's a good idea. The next video, we're going to look at another mechanism, and we're going to begin to see some other aspects of mechanism analysis that will be important as we try to see which are good mechanisms and which are not so good mechanisms. Until next time.